Good afternoon, everyone. Thank you for joining us. Our next session for the day is from Shreya. The topic is generate intelligent insights from your data using graph features in Azure SQL. Shreya is a senior program manager with Microsoft and has been on top of creating this feature in SQL Server for the past 2 years now. I hope you will enjoy the class. It's a really interesting feature and one that I've found, very useful to play with. Take it away, Shreya.
All right, thank you, Mala. And I should have come up with a smaller title. I didn't realize it was a mouthful. So, hello everyone. My name is Shreya Verma, and I am a program manager or product manager in the Azure SQL team. And I own graph database features in SQL and SQL DB backups. So I look at product strategy for both of these features as part of the SQL team. And in today's presentation, we are going to look at the graph database features in SQL and how you can generate intelligent insights from your data using the graph features. So. And I hope you all can see my screen because I'm sharing. So if it's not visible, just let me know. So here's the agenda for today's session. We are just going to look at what are graph databases, what is the relevance of graph in data processing, and what are different Azure SQL Graph database capabilities that you can use. And then we'll look at some demos and some real-world customer scenarios which will help you understand what are the applications of graph in real-world scenarios. So let's start with relevance of graph and what is a graph database. So a graph database, just like a relational database, it's just a collection of nodes and edges. Nodes represent your entities and edges represent your relationships. So in a relational database as well, tables represent your entities and foreign keys represent your relationship. So what is the difference between nodes and edges and graph databases? So here, unlike relational databases, the edges, the relationships, they can easily represent many-to-many relationships. So in relational databases, the foreign keys generally represent one-to-many relationship. But here, the way graph databases are modeled and the way nodes and edges are defined, it is very easy to represent many-to-many relationship using edges. And what that means is a single edge in your graph database can flexibly connect multiple type of nodes to multiple other type of nodes in the graph. And graph databases make it easier for you. The query languages that they support, they make it easier for you to express pattern matching or graph traversal or navigation sort of queries, expressing those in easier form. They make it easy for you with the query language that they support. And graph databases, just like relational, they support both OLTP and OLAP workloads, so analytical and transaction processing. So where can you really use a graph database, right? You must have heard of a relational database. You must be using it for years. You must have heard about NoSQL database. But where do you really use a graph database? So when we were surveying customers, when we built these features in SQL Server and SQL DB, when we were surveying customers, what type of scenarios would they like to use graph databases in? There were 3 or 4 categories of scenarios which stood out, which customers mentioned that they are interested in using in those type of scenarios. The first one was hierarchical or interconnected data. Now SQL supports hierarchy ID data type for many years, and relational databases are known to support hierarchical data for many years. You probably are doing product of bill of materials hierarchy or employee hierarchy or identity management hierarchy already in a relational database. So how does graph model help there? So with evolving data and evolving data applications now in the newer world, like you have IoT data and you have lots and lots of data that applications are collecting now. With those evolving applications, we've seen that hierarchical data is also not, typical tree structure hierarchy anymore. There are complex connections between the hierarchy in different levels. In the same level, nodes can be connected to each other. And in a typical, even in employee hierarchy kind of system, you'll see that a given child node can have multiple parents. Now with hierarchy ID data type or with relational database, it becomes difficult to model that type of data. How do you represent multiple parents for a single node? So in those type of data models, we've seen customers preferring graph models over a relational model. Then if you have complex many-to-many relationships in your database, in a relational database, you would usually model that using a junction table between two tables, but then that increases the number of joins, that increases your query complexities and all that. So with graph models, it becomes easier because you can use a single edge to connect multiple nodes to multiple other nodes. It becomes easier to model and write queries when you have many-to-many relationships in your schema. The third one is when you have complex, highly connected data, and you want to make inferences from that data, which otherwise are not obviously visible to you. For example, you have this Amazon-like retail website, and you want to do simple product recommendations based on customer who bought this have also bought this, and you might also want to add some information there that people who live in this particular area or this city, when they tend to buy this product, they also tend to buy these other products. So based on that, you can make those recommendations intelligent for your customers, right? So you are kind of generating indirect inferences from the data that you have already available. When you have this type of data, then writing queries and generating inferences from that data using graph model can be easier. And we'll see an example of how this can be done later. These are the typical scenarios where we saw customers, using graph models over relational database or a NoSQL database model. Now, what do typical graph workloads look like? What are their queries, right? So graph workloads, like I mentioned, just like relational, are OLTP and OLAP both. They have point lookup queries. When you talk about OLTP queries, they have point lookup queries. Like, for example, in a social network, find me all my friends. So you know that you are starting from me and you are going to try find the people that are connected to me. Or in find me in an employee database, find all the people reporting to this manager, a given manager. So that type of point lookup queries, even graph databases have that. And they also have BI or aggregation queries, right? They can also support that. So you are going to scan the entire graph and you are going to say, oh, in my city, in this demographics, find me the number of families connected to each other, or find me an average age of each of the family, right? So that type of aggregation queries you would do. And they also, another type of analytical query, which is specific to graph databases, is graph analytics or graph algorithms. So for example, shortest path, page rank, community detection, or betweenness centrality, things like that. They are all graph specific algorithms, which graph databases support. Some of them, a lot of algorithms are supported out of the box natively. So you can just use them, and some of them you can write using stored procedure or the query language that the databases support. So now that we have seen what is a graph database, what are typical graph workloads, and where you can use a graph database, now you would ask, why did we build these features in SQL, and what is SQL Graph? What does SQL support in terms of graph web capabilities, right? And why did we add it to SQL Server at the first place and not create a new database? Because this definitely looks like a different type of database. So why did we integrate it within the relational engine? Because SQL is relational. So our philosophy around that was very simple. We decided we'll embrace and extend. When we were deciding to build this SQL Graph features, we were surveying customers, and all of our customers unanimously said that we don't want to use different type of products for two different products for like data processing. Pay twice the licensing cost for two different products, maintenance costs. So they all wanted one system where they can make use of both relational and graph systems, right? And then when we looked at SQL Server is a mature product. It has 40 years of academic and industry research backing it. And it also has a highly evolved ecosystem, like we have tools and community and everything around it. So it was a mature product, and adding capabilities to it only made sense. Then SQL is also a trusted product, trusted by millions of customers already with their enterprise workloads and mission critical workloads. So adding graph capabilities to it only, since it is already trusted by customers, graph capabilities, if we add to it, it only made sense at that time. And then with SQL already is a system which is built to support hybrid or on-prem or cloud workloads. So by using the underlying infrastructure, now for Graph also we can support all type of workloads. So you can write an application which is hybrid. Part of it you are running on-prem, part of it you are running on cloud, and then these are all talking to each other. Or you can completely build a cloud application and it's fully supported in Azure SQL, or you can build on-prem application. These features are also available in SQL Server. And then there was enough research which proved that relational engines can also support graph database processing. You don't really need a dedicated or a native graph database to support these graph algorithms or graph queries, OLTP or aggregation queries. Relational databases are evolved systems, and they can do the processing required to support graph database scenarios. So since there was enough research backing it, we decided that we'll build all these features in SQL instead of building a new product out of it. So now let's look at what is SQL Graph and what are the features that are supported, graph database features that are supported in SQL Graph. So like I said, Graph is a collection of nodes and edges. So now you can create a schema in SQL database, a graph schema, where you can create your nodes and edges. And now since we started with a relational engine, we store these nodes and edges in form of tables. We use the underlying storage engine. So we store them in form of tables. What that means is SQL Graph is structured. It's not unstructured. You can't bring NoSQL like key value stores. It is structured. You have to define your schema. You have to define how your nodes and edges will look like. And then to support creation of these nodes and edges and to support navigation, easy navigation through these nodes and edges and traversal queries, we introduced DDL extensions and query language extensions. So DDL extensions which let you create these nodes and edges or node and edge tables, and query language extensions which let you write the match queries for navigation or traversal. Then, like I said, the tooling and ecosystem which is available with SQL Server, which was already available with SQL Server, is also available with Graph. So you can use all your tools that you're already used to, like SSMS, the same query language, T-SQL, and things like replication, things like column store indexes or high availability or machine learning using R and Python. They just, or security features, they just work out of the box for graph database features. Now let's look at how would you create these nodes and edges, and then how would you query it, right? So creating a node which represents your entity in a graph is very straightforward. You just create a table with all the data types that you want in it. And in the end, you just add the as node syntax to it. So this tells the engine that this is a special type of table. It's a node table, and it will be used for a graph schema, right? And what happens when you create a node table? Why do we have to use this special syntax? What is happening behind the scenes when you are creating a node table? So when you create a node table, along with all the user-defined columns that you have in your table, what we do is we create one implicit column, which is called $node_ID. This is a combination of your table name plus internally generated sequence. And it uniquely identifies each node in the database. And when you create this table, we also create an implicit index, unique index on this node ID column. And this index later on helps us, in faster navigation for graph queries. But you can also define any indexes of your own on this table. And if you define a unique index of your own on the node ID column, we don't create the implicit index. We detect that a user has already created a unique index, so we don't duplicate. We don't create two indexes for them. And all type of indexes or constraints that you can use on relational tables are also supported on these node and edge tables in graph tables. So any constraint, any index you can define here on this table. Any data type that is supported by relational engine is also supported by graph engine. So you can define, when you're defining your user-defined attributes here or columns, you can use any data type that you generally use. Now let's look at creating edge table, and please feel free to ask questions in between if you have any. I'm happy to answer. So creating an edge table, just like node table, it's pretty straightforward. You will just write your create table syntax, and then in the end you will specify as edge instead of as node. This just tells the engine that this is a special type of table. This is an edge table. This is a relationship table, which will be used to connect, two nodes. Now, in an edge table, you can have a user-defined attribute. You may or may not have. You can, or you don't necessarily have to. You can create an edge table without any attributes also. So, like here, the friend of edge does not have any user-defined attributes, and this will still work. Now, what happens when you create an edge behind the scenes? So just like in node table, there was one implicit column $node_ID. Here we create three implicit columns. One is $edge_ID, which is again a unique identifier for each edge in the database. And we also define a unique index on this one, implicit unique index on this one, if users have not defined any. Then $from_ID and $to_ID are the two columns which will later on, when the data is inserted into edge, show which nodes this given edge is connecting. So if you notice, when we created the edge table, we did not define which nodes this edge is going to connect. What that means is a given edge in SQL can flexibly connect any node to any other node. And what that means is you can have only one edge table in your graph, and you can use to connect that to every single node to every other node in the graph. However, we don't recommend that, because then you are making your edge table very big. We recommend that you define one edge table per relationship type in your graph. Then when you insert the data into the edge table, you are basically telling the engine that these are the two nodes. Here are the node IDs that this edge is going to connect, right? And then you can insert the user-defined column values, whichever. You can have those user-defined columns in the edge. That means your edges can have attributes associated with it. So you can filter later on in queries based on these edge attributes, and so on and so forth. Again, all your constraints, indexes, all of them are supported on these edge tables. All data types are supported in the edge tables. There is no restriction. And when I say indexes, this includes the column store indexes. So you can also define clustered column store or non-clustered column store indexes on the edge table. So if you have analytical workload aggregate queries, defining those on your node and edge tables will be very useful. We have already seen few customers using clustered column store indexes in production in their workload, and benefiting from the performance of the clustered column store index. One thing that I forgot to mention here is that when you create node and edge table, you see that this edge ID and node ID columns are actually combination of the edge and node table name and an internally generated sequence. So when you select from the table, you see this JSON printed out, which shows you that this is a edge type table, the schema is DBO, the table name is bot, and then there will be some sequence here, integer. So it looks a string or a JSON value here. But internally, it is stored in form of begin, so it does not have a very big memory footprint, and it's easy, it's quick, fast access. Now, on an edge table, we saw on the last slide, we saw that the edge can flexibly connect any node to any other node. But you can also define some constraints on edge table. Now, we introduced some edge constraints in SQL Server 2009 with the SQL Server 2019 release. And what that does is it helps you enforce, specific semantics on your edge table. So, for example, you want to, in your schema, you want to define that the bot edge can only connect, a customer to a product, but no one can insert a record through which they are showing that a product has purchased a customer, right, or the other way around, or something else. Someone else has bought a product. If you want to define those type of constraints that don't allow these other type of inserts or don't allow connection between these two specific type of nodes, or only allow between these two types, then you can use the edge constraints for that. And another benefit of edge constraints is that you can also have this clause on delete cascade, which will help you maintain data integrity. So what this does is, so if you have a customer who has bought a stock item, now that customer left your website, so you don't need their record anymore. So you're going to drop the customer record, or maybe you no longer support the stock item which is there. So you want to delete the stock item record. So when you delete a node or a given node in your graph, all the connected edges to it will remain there because they are in a different edge table. So you should delete them on your own to maintain the integrity. Otherwise, you will have a bunch of dangling edges in your graph. Or you can use the edge constraint and you can define on delete cascade. So what happens is when you delete a node, any incoming or outgoing edges from that node will also be deleted along with the node deletion in a single operation by the database. So that will help you, enforce semantics and also maintain data integrity in your graph. It's a very important feature actually, which is pretty cool. Now, how do you insert data into graph tables? Inserting is quite straightforward. Into the node table is very straightforward. Node ID column is an implicit column. You don't have to necessarily insert data for it. All you do is you insert data into your user-defined columns, just like you would insert into a regular table, and those values are inserted. But while inserting into an edge table, because we are not, when creating the edge table, we did not necessarily define which nodes this edge is going to connect. When you insert into edge table along with the user-defined columns that you have, you also have to insert values for the from ID and to ID columns. These are basically the node IDs that this particular edge is going to connect. So here in the example, what I'm trying to show is that I'm trying to insert a record in the bot edge, and I'm saying that customer node ID, where some customer ID, they have bought a stock item with some ID, and this was the purchase count of that. So I took the customer's node ID and I took the stock items node ID and I inserted that into from and to respectively. So that is how you insert data into your edge table. Now let's look at the query language extensions. And we introduced back in 2017, SQL Server 2017, with the release of that, with the release of SQL Server 17, we introduced this match predicate in T-SQL, a built-in predicate. What this does is it helps you write your navigation or traversal queries, and it supports ASCII art style graph traversal syntax. So with arrows and simple syntax. Here's how it looks like. So your select statement will be regular select statement that you usually write. You have select, then you project bunch of columns that you are interested in. Then you have your from clause, and you select from the tables or the graph nodes and edges that you are interested in. And in the match clause, here in the where clause, you use your match. And in there, you are basically saying that find me all the customers who have bought a stock item in this. So we are going from customers to stock items via the bought edge. We always go from one node to another via an edge. We never go from, you can never go from node to node directly. You need an edge in between. And the arrow of here in the match syntax signifies the arrow of the edge. So graph in SQL is a directed graph. That means each edge has a direction. You cannot create an undirected graph in SQL. If you have a bidirectional graph, that means from node A to node B, if an edge goes from node A to node B, and the same edge goes from node B to node A also, then to represent that type of bidirectional relationship, you have to create two edges in the graph. So you would insert two records, one that is going from A to B and the other one that is going from B to A. And here in the match also, when you are writing the match, it just signifies the direction of your edge. So basically, you're trying to find all customers who have bought a stock item, and the stock item being all-purpose bytes tag. So you will go from customer to stock item to find the customers via the bought edge. Now there are few new features that we did in back in 2019, which are actually very useful in some of the graph database scenarios. So one of them was view or derived table support in match query. And what this does is it helps you with the help of this feature, you can write queries where queries like, find me anyone that I am connected to in my graph. So for example, in LinkedIn, on LinkedIn, you want to find anyone that I follow. Now that could be a person that you follow, that could be an organization, or that could be a group that you follow, right? So usually what you would do is you would first find the people you follow, then you would find the organizations you follow, then you would find the groups that you follow, and then you would aggregate that data, right? But with the help of this view and derived table support in the match query, inside match clause, a match built-in, you can make it a bit easier writing these type of queries on an ongoing basis. So what you can do is you can either define a view or a derived table for the heterogeneous types that you want to query. And then you can use that derived table or view in the match clause to get your results. So usually, like if you are familiar with Neo4j or Gremlin, they support a star syntax. So find me anything that I'm connected to. So they start with you, person, and then connection, and then star, which shows find me anything. In SQL, however, we did not support the star syntax. So what we did was, in place of that, we did view or derived table. It had performance implications, so we started with view or derived table. A bit conservative. So how you do that is, for example, here in my scenario here, what I want to do is I want to find a full contact information for Alice. Now Alice has 3 pieces of contact information. She has an address, she has a phone number, she has an SSN. So if I want to find all of her contact information, I have to query address first, phone number, and then SSN, and then combine the information. So instead of that, what I do is I created a derived table called all contact info. And in this derived table, I pulled in the information that I needed. For example, I pulled in street from the address. I pulled in phone number from her phone number record, and I pulled in SSN from her SSN record, just number. And then I used a union all operator to combine all of this data, and then I called it all contact info. Now, when I write my match query, I could have created a view also with this name, all contact info. And now when I write my match query, what I do is I say, my customer is Alice, and find me all contact info of Alice. And this customer could be Bob, or this customer could be David, and we can run the same query and get the full contact info for them. Another feature that we built was shortest path, or you can also call transitive closure in Graph. And what it does is it helps you find a shortest path between any two given nodes in your graph. And it lets you do multi-hop navigation without specifying the number of hops. So for example, in this graph here, I want to find the shortest path between Bob and Mark. And I know that they are connected via multiple routes to each other. However, I don't know how many hops do I have to make to get to Mark. What is the shortest path, right? So how do I write that type of query in SQL? So you can use this shortest path syntax to write that type of query when you don't know how many hops you have to make to get to a particular entity in your graph. So here what we do is we shortest path is like another function or built-in that we introduced. You can use shortest path inside match. And the way it works is basically you say start from a customer. These are all customer nodes. So start from a customer, traverse via friend's edge because they are connected to each other via friend's edge. And then keep traversing other customer nodes until you find Mark. So what our shortest path implementation is, it's just a basic Dijestra's shortest path algorithm. It's breadth first search. What we do is we start from Bob, we fan out, we find first level connections. If we find Mark in the first level connections, we return. If we don't find Mark, then we take these first level connections, we fan out from them, and then we try to find if Mark is in the next level. And as soon as we find Mark, we quit. We don't continue traversing. So that's the shortest path, basically. So what happens is in this one, in 2 hops, we find Mark. So we quit at that time and we return the path, right? So what's happening here is you start from the from customer, but then the friends and the to customer here, they are edges, and they are the edge and node that you will keep traversing again and again repeatedly or recursively until you find your destination node. So what that means is they hold a special meaning, or they have a special semantic here. And because this is a path that you are continuously or recursively traversing, whatever is coming out of this combination, the friend edge and the node, that is a collection. It's not a single edge or a single node coming out. It's a collection of path, collection of edge and node. It's a path that is coming out. So to select data out of it, it's like a window in that path, right? Select data out of it. You have to tell engine that this is a special collection that I'm pulling information from. It has a special meaning. So what we tell the engine, the way we tell the engine that it has special meaning is we use this for path syntax in the from clause. This basically tells the engine that these 2 things are going to be repeated again and again. This pattern is going to be repeated again and again until I find my destination node. And then to select data out of this pattern, out of this collection, you have to use these aggregate functions, the string ag, count, sum, average, all the aggregate functions, they are supported on with shortest path. And we'll see some examples later on in the demo. So now let's look at some examples in action here, right? So the first one that I have to show you is the product recommendation one. If you remember, we talked about it in the first slide. And there was a simple scheme. Here's a simple schema. We have a customer who bought a stock item. It was supplied by a supplier. A supplier is from a location. The customer is also from a location. And then customer can be friend of another customer. So we have some social aspect to it, right? And now this is a very simple schema. Now based on this, we want to write product recommendations. People who bought this have also bought this. So if you go to Amazon.com or Walmart.com or any online retailer, you will see that when you buy a product from them, they usually at the bottom of the page, they'll show you people who have bought this. They have also bought these other products. So this recommendation is made just to entice you to buy more products from them. But it's a pretty good marketing strategy. So if you want to write that simple query based off of this schema, you can do that easily in a relational database too. This looks like a straightforward schema, can be easily created in a relational database using tables and foreign keys. But if you want to if you were to create the schema in a relational database and you were to write that query, product recommendation query, that query will look like this. So you take your current user who is buying a product, then you find out which product they are buying. Then you find other users who have bought this particular product. So once you know the other users who have bought this product, you go and find the other items that these other users have bought so that you can make recommendations. And once you have a list of other items that these other users have bought, you go and make your final recommendation to your current user who is buying this product, right? That look, people who have bought this have also bought these other products from us. So you might be interested in buying them. Now this is 56 lines of code, and it's not easy to write and it's probably not easy to maintain also, and extend in future. Now, what happens when you write with SQL Graph, the same query? So this is the query that product recommendation query. This is how it looks. It is 17 lines of code, as you can see. And what we are doing here is we are starting with customer. We are trying to find all the customers in our database who have bought this item. This item being the current item that our customer is buying. And then once we get a list of all the customers who have bought this item, we go and find the list of other items that these customers have bought. These become our recommended items, right? And what I did was just filtered the products that our current customer has already bought. So I filtered that out, and I already filtered the products that they must have bought in the past, right? So we don't want to recommend the same products to them again. So I just filtered that out. But with the simple query, you can make those recommendations and then finally pass on the recommendation to the customer. So that query becomes so simple, in which you want to make inferences from what's happening. Now, extending this query is also very straightforward in graph implementation. So let's say you want to find out the suppliers who have supplied the recommended items, right, in your schema. So imagine extending that one in here. Like you will have to write another city for that supplier, get that information, combine it, join it with the data here, and extending it again will be like some work. But here, what you do is you already have that recommendation query. All you do is you extend the query by adding one more pattern to your graph query, saying, find me all the suppliers, find me all the suppliers who have supplied this recommended item, right? So where this recommended item was supplied by a supplier. So all you did was you extended your pattern. So what this does is basically the way you will write your query on a whiteboard is the way you will write your query in here in T-SQL. So it makes it easier for you to visualize and to write your queries. Now that was like just a sample of queries that you can write. Now I want to show you some real scenarios, real demos. And for that, what I did was I took a Yelp dataset demo. I prepared a demo from Yelp dataset. And this we downloaded from Yelp website. So I just wanted to give them credit for that. And it's a free dataset, but you cannot, use it for commercial purposes. So just wanted to mention that disclaimer here. What we did was we took their database. So there are users in this data set who are connected to each other. And these users are writing reviews for a restaurant or hotel or places they are visiting. And they might like a place or they might leave a review for that place, right? So that's basically, it's a pretty simple, straightforward schema. Now let's look at some demos based on this schema. So one of the things that you might do in your graph database is simple filtering based on attributes or simple point lookup queries, right? So let's see how these point lookup queries look like using the graph implementation. We have seen an example on the slide, but let's just quickly look at a very simple query. So what I'm trying to do here is I'm trying to find all the people who are friends with this user ID. So one point lookup query, find me people, friends of this person. So person is coming from final user and the friends are also coming from final user node. So find me all the friends of this person. And this person is the person with user ID, this. So we just quickly run this query and I've created this database on Azure, and this tells us that this person has so many friends. There are about 108 people, 108 rows which were returned, right? So they have 108 friends in the graph, and this just quickly returns us that. So where will be these type of queries useful, right? So some of the scenarios that I could think of, which example scenarios that I quickly noted down here is like, find me the people that I'm connected to in my graph, in a social network, which we just saw an example of that. In a CRM type of database, find me all the opportunities or the accounts of the sales people that I'm connected to directly. Or in a HR type of HR employee database, a query will be find all the employees reporting to a given manager. Or in a identity management type of this database, you would say who all have permissions, or who all have permissions for this given folder or a role, or things like that. So there are some simple scenarios. There are some example scenarios where you would write a simple 1-hop, 2-hop query based on a filter. Right. Now, next scenario is finding paths in a graph. So we looked at shortest path on few slides ago, and we looked at how you can use that syntax to find a path or shortest path between two people in the graph. Now let's look at one more example here. So here what I'm trying to do is I'm trying to find shortest path between these two users. I don't know how they are connected to each other. Or on LinkedIn, maybe you are trying to make association with somebody, but you don't know how you are connected. So you go visit their profile at the bottom of the page. There's somewhere they show at the side of the page. There's somewhere they show you are connected to them 3 levels away. So that's the type of the query. So you want to make connection with somebody, but you want to find out what is the best route to make connections with them. What is the shortest path through which you can be connected to them. So using this query, you can do that. So what this query is doing, it's shortest path. So there you go. So we say that I started from user Sally, and she's connected to Christopher via 2 hops. And to make connections with Christopher, Angie is someone she knows, so she can go and make connections with Christopher via Angie. She's connected to them via Angie. Now, what this query is doing is we start from origin user, which was Sally in our case, and we keep going. We try to find the shortest path until we find person 2, and our person 2 is here. So we put the filter on that. This is how you put filter on the destination node. You make the shortest path query a subquery, and in the outer query you put the filter on the destination node, and we push this filter down when we optimize the query. So it's properly optimized at that time. What plus here means is in the shortest path syntax. Let me make it bigger so that you guys can see. What plus here means is keep traversing the graph until you find my destination node. So instead of plus, you can also write 1 comma in curly braces. You can write 1 comma 5. What that means is keep traversing the graph until you find the person that I'm looking for, or if you reach 5 hops. 1 comma 5 is anywhere between 1 to 5 hops. So whichever reaches first. Stop the recursion as soon as you have exhausted 5 hops, or if you find the person at the first hop itself, then stop the recursion at that time. But plus means you are actually going to traverse the entire graph until you find the destination node that you are looking for. So if this destination node was like 12 hops away in the graph, we would have kept traversing the graph for 12 hops. So this is a dangerous thing to use. So use it wisely in your graph. If it is very big, then we recommend that you stop the recursion with using the number of hops, like using the curly bracket syntax, using 1 comma 5, because even this Yelp data set is a very big graph. It's 2 million nodes and 19 million edges. So even using in this data set is not recommended. But you can use it if the syntax is there. All right, now going back here, So where would you use, or where is the significance of this shortest path, right? So we have a published case study of a customer who are using us in production. They are actually energy company, and what their scenario was, if a particular transformer or some energy station is down, they wanted to find out who all are the customers impacted because this particular station is down. And if they are impacted, what is the best way, or which is the closest station we can read out them to, So to answer these type of questions, they are using SQL Graph in production. And they have actually pretty big queries. Some of their queries are like 96 hop queries, if I'm not mistaken, and they are successfully running their workload in production on SQL Graph on Azure SQL actually. And they are using a hyperscale database for that. So the best thing is that all the SQL features are also available to you. So like this is available on hyperscale, this is available on managed instance graph features. So wherever you are using SQL, you can use Graph. Now looking at, Mala, is there any question?
There's no question yet, Shreya. Nothing that I can. Yeah, sorry.
Yeah, for a second I thought maybe I lost the connection.
No. Sorry, they're all being very quiet.
All right.
But they're all here, which means you have an audience. Go ahead.
Okay. So let's look at one more scenario, which is how do you query complex data models? So here I have an example in this data set again, where you want to, let's say you are visiting some place for a movie or for a game, and now you're done with your movie and your game, and now you want to find out restaurants near you where you want to go and dine. And but you don't want to go to any restaurant. You probably want to go to a restaurant which one of your friend has recommended, right? So one of your connection direct, or one hop or two hop away is somebody who is close friend to you. They have recommended that place, and it's a nice place, and so that's why you want to go there. You just don't want to go and randomly eat at some random place where random people have left reviews. So we'll use this type of query for that. What we do is we find all our friends which are one or two hops away in the graph, and then we see if they have left reviews for something which is close to me. And we run this query, and based on that, we decide which restaurant we want to go. So we saw that these people have left a review for a restaurant which is near me. And what I did was to find the restaurants near me, to get a list of restaurants near me. I actually use the spatial syntax in SQL, to find anything which is near me, within 5 miles near me. So this, you can combine, just showing that you can combine different features in SQL to, get a list of things, or you can combine different features like spatial and graph in SQL to make sense out of your data. So in this query, we are just doing that we are trying to find the restaurants near me, and we are trying to see if there are people in my network who have left reviews for that. And this query just shows me that for the restaurants near me, these people have left reviews. Oh, and I know that these are my good friends, so maybe I can trust them and trust that review and go and visit this place. So one example, in real life example of such query is CRM, dynamic CRM. They also use us in production for their workload. And what they wanted to do was in their CRM database, they wanted to find out people, like for a salesperson, if they are starting to work on a new opportunity or a new account, they wanted to find out how am I connected to this account or an opportunity. If I'm not directly connected, is anyone that I've worked with in my previous accounts or previous opportunities, are they connected to this new account? How can they introduce me to this new account? And then they also generated insights using the graph features for customer or market segmentation or customer segmentation. For example, when they did online marketing for their for their products, then who all are, type of opening the emails, which market segments are more aligned to what type of products and things like that. So that type of analysis they were doing, complex analysis they were doing using SQL Graph. Now, the last scenario that I want to show, because we talked about graph analytics a lot, and we said graph databases support analytical algorithms out of the box. So we saw an example of one analytical algorithm which is supported in SQL natively, which is shortest path. But how do you do others? So I have an example here of PageRank. And the way I'm using PageRank is finding top influencers in my database. So in my Yelp database dataset that I have for the demo, for example, I want to find who are the top influencers. Top influencer being the people who have maximum number of connections, right, in the graph. So that means their outreach is to maximum number of people in the graph. So if they were to write a review for my business, or if they were to like my business, that means maximum number of people in my graph will see that they have reviewed. And that means a lot of people will know about my business, right? So it's good for my business. So I want to find out top influencers in the graph so that I can, devise a marketing strategy, or I can reach out to them and I ask them to leave review, offer them some free products so that they leave good reviews for me. So how do you do that? How do you find top influencers in your graph? So PageRank is not supported out of the box in SQL, like we don't have a function for that. But T-SQL being a Turing complete language, you can implement anything using a stored proc. So that's what we did. We have an implementation of PageRank here. And this is all uploaded, by the way, on GitHub, and I have links later on in my presentation to the GitHub documents and demos. So you can download and play around with this. So this is a PageRank implementation. What this is it's a simple implementation based on the number of out degree a person has recursively. So you found first level, then next level, then next level. Based on the number of out degree a person has, we decide the rank that person has in the system. And the person with highest number of out degree has the highest rank. It's a simple PageRank algorithm that Google uses for search, in PageRank, their ranking system. It's the same algorithm. So we start running it, and what this does is actually it's going to scan the entire graph and then come up with PageRank for everyone in the graph, right? So it takes, when I run this, it takes a couple of minutes to run this query. So what I did was I ran it in advance and I kept the results here so we can look at the results while that query is running. What this does is it just basically prints out all the user IDs for me and the out edge count. So this number has a maximum, this person has maximum outreach in the graph. And it tells me that it tells me as a business owner that if I reach out to them, these many people will find out about my business as soon as they provide a review, right? So you might have some scenarios like that in your use cases, and this might be useful there. So let's go back to our demo here. This might finish in like a minute or so. It's 51 seconds right now. So let's look at the quick summary of what we have seen so far. So we saw that many real world use cases, not just social networks or networks, computer networks, or not just typical scenarios that you might have thought of as graph database scenarios. And not just those scenarios benefit from graph databases. There are some real world scenarios where you can actually use graph database and benefit out of it. So, and we have looked at them like product recommendation, which you would think typically of, relational database scenario. Even there, sometimes you might want to use graph databases in that cases. And then with SQL Graph, you have this seamless blend of relational and graph models. So we saw that in the Yelp example I showed you, that I use the relational and spatial features to find out hotels near me, restaurants near me. And then I use graph features to find out the friends who have recommended these restaurants near me, right? So that I can decide which restaurant to go to. So you can combine both your relational and graph models at the same place. And you can query across this data at the same time. Like these are not in two different systems. So that you have to query at one place for one query, relational type of query, and then you have to go to another system to query for graph. You don't have to do that. You can be at one single place and query across your relational and graph model. And SQL Graph also offers you the tooling and language, like I mentioned before, the same system, same ecosystem. So there's no learning curve. You don't have to, learn a new language, new ecosystem to get started with it. Some of the customers who have worked with us and adopted SQL Graph, they got their application up and running in a matter of a week or 10 days. It was so fast for them because they were already SQL customers. So they were well aware with the optimization and implementation part of it. So they were up and running in 10 days. And again, I can't stress enough that SQL already comes with industry leading security, performance, availability, and read, scale, and features like that. So you can just benefit out of that out of the box because this is built into the relational engine. The graph engine is also built into the relational engine, and you can just benefit out of all these features, which you would otherwise not get with some native graph databases. And we saw that you can combine relational and graph query workload with SQL Graph. So with that, like I said before, I have samples and demos, everything available on links, and I'll share this slide deck with later on with the community, so you can go and download these samples and demos from there. We have lots of other samples for other features also documented, and here are links to the documentation that you can go and read, and blogs and samples that you can look at. And I think with that, I am at the end of my demo here, my presentation.
Do you have any questions for Shreya? All quiet. Shreya, I wanted to ask you if there are any plans to put some of these tables in memory, like make it hackathon based.
Right. Yeah, there are. I mean, we do know that it is not hackathon is not supported with graph tables yet, and it is on a roadmap, but it is not on our immediate roadmap. So I can't tell you that it will be there in 6 months or a year yet.
Oh, okay.
So
would you be able to share what is on the roadmap?
On the roadmap, yeah, we do have few things we want to bring in this. We also do not have replication support for graph tables or graph nodes and edges yet, so we want to bring that. Then we do want to bring in visualizations. We don't have native visualizations for graph. So
that would be very useful. Yes.
And then we also want to support some analytical algorithms out of the box. So all of this is on roadmap for graph.
One thing I would find personally useful also is if shortest path was able to pull all the shortest paths and not just one.
Yeah, actually we've received that, and we also received feedback that we want weighted shortest path. So this shortest path is not weighted yet.
Yes.
So yeah, that is also something improvement that we want to do with shortest path.
Cool. Thank you. All right, everybody, we're signing off now, and the last session with Cindy Gross will start in another 15 minutes. Thank you.
All right. Thank you, folks. Bye.